Okay, let me repeat since some more people join. Okay. Hello, everyone. My name is Calvin. I'm here to be the main speaker for our SciML workshop. And for this week, we'll be introducing some of the basics of scientific machine learning. Okay. A bit more about myself. I did a statistics major as well as a math and CS minor in the Faculty of Arts and Science, St. George campus. I'm also an international student from the Caribbean and EU and graduated recently in November 2024. And for my last semester, I went on exchange to ETH Zurich on the suggestion of one of my computer science professors. And at there, she connected to me to one of her previous students who's teaching the cloud computing and large-scale LLMs course. And I also took some other courses there, like a scientific machine learning course, which is what this workshop is going to be based on, as well as a modern diffusion theory and modeling course. When I was also over there in Europe for the 6 months, I also participated in a Gen AI hackathon there, where I managed to place first place in Switzerland with a team of 2 U of T students and 1 local, even though we're technically all Europeans. And we placed 4th overall in Europe in the end. As for my other experience, I have like 2 research projects under my belts. One in weather modeling, which is going to be relevant for this workshop, as well as another one that's a bit more applied into all these 3 fields I study. I got accepted to the Canadian Undergrad Math Conference with a talk. Based on these experiences, I think you can see why they elected me as the academic director of scientific machine learning and generative AI now. So that's enough about me. As for our other speakers, our first guest speaker is going to be Ben Mosley. He was my professor and instructor at ETH Zurich on scientific machine learning. He completed his PhD at Oxford on the topic, and his thesis serves as one of the reference points that this workshop will be based on. During his PhD, he served as an intern at NVIDIA. Afterwards, he also was the head director of NASA's Frontier Development Lab for 4 years. And I'm also going to give you a bit surprise now because I managed to get another surprise guest speaker yesterday night. Let me introduce you to Patrick Ridger. He's also did his PhD at Oxford on scientific machine learning as well, and also on neural differential equations, a method that was pioneered here at U of T, along with some other generative AI methods that are taking over the computer vision world. He's an avid coder and a so-called ML wizard at a startup called Cradle.bio and specializes in biological machine learning nowadays. In his free time, he likes to contribute to open source software for machine learning, especially JAX, which is an alternative to PyTorch and TensorFlow, and is supported by Google. More recently, he's helped and joined a startup called Cradle and raised over $100 million in funding last year on more so the protein language modeling. Both of our speakers will be presenting later in early April. So hopefully that's not a problem for you guys. Okay, as for like the aims of this workshop, I just want to make you guys like aware of the recent successes and applications of scientific machine learning and know how we can use these methods to solve like some of the fundamental problems that scientists face. And near the end of the workshop, I'm going to be giving a coding tutorial where you guys can familiarize yourself with the design and coding of these methods as well in PyTorch. I can guarantee that all these methods can work in Google Colab, so it works on even your iPad. And this is something you can't really say for some of these traditional methods, which requires like some of the biggest and fanciest supercomputers in the whole world. Now, along the course of these 4 weeks with me, you're going to be picking up some of the key scientific ML concepts and general themes with it. And I hope by the end of this course or workshop, you'll understand the pros and cons of using scientific machine learning in your applications. So before we get into scientific machine learning, I first want to talk about some of the recent successes we've seen in machine learning in general. So a while ago in like 2016, Google DeepMind released a AI model called AlphaGo based on reinforcement learning and deep neural networks and Monte Carlo tree search. And what this model showed was that despite the complex decisions that are presented to you on this game of Go, I'm not too sure if you guys have heard about it. Have you guys heard about it? Okay. I guess it's been a while. So basically, in this game board of Go, there's a huge possibilities of options to take, and when you're playing against an opponent, you have to pick the best possible outcome to win in the end. And this is much more difficult than chess, which has been solved since 2000 by supercomputers. But what makes AlphaGo so different is that you don't really need a big stack of CPU supercomputers. Instead, you can run stuff on the GPU instead with deep neural networks, as well with some clever tree search going on. Now, I'm sure you can see like I'm sure you guys can recognize some of these names on the paper, like Chris Madison. He's currently a professor at U of T here. Originally, he started off as a student of Hinton and went on to join him at Google DeepMind doing reinforcement learning. Nowadays, he's back at U of T and he switched his research focus instead of reinforcement learning. Well, it's technically still interest, but his new interest is scientific machine learning, more so on the medical side nowadays. And there's also this other guy of Ilya Sutskever, I'm sure you guys have heard about, right? Now, this is just the success we've seen in like RL like a couple of years ago. But more recently, we have seen some explosion of success in content creation for like computer vision. It just started off like about 3 years ago when OpenAI released their text-to-image model called DALL-E, where you literally just give it a description string, and it'll give you an image output that satisfies the contents of that description. At the time, this was revolutionary and hasn't really been done before. And since then, how these techniques have managed to become so powerful was this kind of a new idea called diffusion models that came out relatively recently. And using these diffusion models, we can generate images from basically nothing in there. And so for more recently, in last year, we have Stable Diffusion, a company based in the UK that released their own diffusion model called Stable Diffusion 3 that's rivaling OpenAI's DALL-E 3 model as well, and it's also open source. Additionally, I'm not too sure if you guys have heard about Flux. It's another diffusion model, more so about on flow matching, if I remember correctly. It came out in like November, and it came out from a German tech startup as well. So there's a lot of interesting avenues to explore, especially from all over the world in these fields. And now I'm sure you guys have heard about LLMs, like this one. This is called like DeepSeek V3, came out in like Christmas. What's so interesting about this one compared to like OpenAI's like GPT series is that it manages to deliver a trade-off between, well, more so there's no trade-off between quality and performance and price. Here we see that DeepSeek V3 at the time of release had state-of-the-art LLM performance across all these 5 benchmarks we see here. And MMLU Pro is a language benchmark. GPQA is similar. And then we have the 2 math benchmarks in the middle, and the last 2 are coding benchmarks as well. Here we see DeepSeek sweeps the board and claims first place on all categories. And what's so impressive is that DeepSeek at the time was a pretty small company with only 200 AI researchers, which is a fraction compared to these other models and teams from like Meta's Llama team and OpenAI's GPT team and Anthropic's Claude team as well. Furthermore, what's so innovative about this V3 model is that it's made use of a combination of innovative and fast methodologies, such as multi-head latent attention, which provides a massive qualitative speedup and also quantitative speedup in performance, which is very rare these days to see. It introduced a mixture of expert architecture. Now, there's been a little bit of use of this, but there hasn't been we haven't really seen the best model been an MOE architecture in quite some time, like probably like 2 or 3 years since a French company has done it. As well as that, DeepSeek has engineered a method to overcome the next token problem. So I'm sure you heard that how these large language models works is they just predict the next tokens or words in a sentence. That's how they are able to do all these tasks. Here, the DeepSeek team managed to do multi-token prediction. So what they do, instead of predicting the next token, they predict the next 10 tokens or so. And combine that with some other like system improvements and like the key value caches that reduce the amount of GPUs required and the amount of memory required, we can see that this enables the pre-training of DeepSeek V3 on 2,000 nerfed H100 GPUs for just 14 days at a rental cost of $5.6 million. I'd also like to note that this is the first notable use of floating point 8 training at this scale, because these GPUs have only came out in the last 2 or 3 years. So far, we haven't seen any of the previous top models use these floating point 8 models. And what's so beneficial about these FP8 models that these reduces your memory requirements by half and also speed up your token output by doubling too. But one of the key challenges to enable FP8 on these models is that the software stack for these LLMs are not mature enough, as these GPUs are still brand new, like only in the last year or 2 or so ago. So the speed of innovation is taken very rapidly. In fact, 4 weeks later, DeepSeek released their first reasoning model called R1. What's so impressive is that besides just sweeping the board again against like OpenAI's own reasoning model called O1, it's that it manages to do so with a brand new innovative RL method called Group Reduced Policy Optimization, GRPO. And what they demonstrated in their paper was that GRPO scales fast and cheaply at the same time. This enables DeepSeek to adapt the V3 base model and easily converts it to a reasoning model quite quickly. So in some independent research benchmarks from academics, people have found that when we use GRPO on a base model, you can get immersion capabilities out of these models for like in a few hours for only a couple of like dollars, like $50 at most. And we can see a substantial increase in performance, sometimes like 10x to like from something non-significant like 0% performance increase up to like 50%. Because of these innovations, DeepSeek caused a disruption in stock markets, in the New York stock markets, wiping out nearly $1 trillion in market capitalization. Furthermore, last week, DeepSeek introduced a nightly discount rate of 75%, and even after these discount rates were applied, we can see that DeepSeek maintains a profit margin ratio of 545%, which is a huge industry achievement. So it's pretty fast, you know. And then there's another one that just came out 50 hours ago. Here we have Alibaba's Qwen AI group releasing their new 32B model, QWQ, this is only 5% the size of R1, and this is dense. But even if you compare this dense model to the activated parameters of DeepSeek's 37 billion, this is still a 15% shrinkage at the same quality performance. In other words, basically what we see from these rapid innovations, we can see like these combination of methods from like natural language processing and RL keep on performing and keeps on scaling. Now, there's also been some reports that Alibaba and Apple are collaborating together for a iPhone AI model as well, but we'll see soon about that. So that's been the successes in machine learning you probably know and kind of hear, but I want to tell you about something that's been in the works suddenly in the background. So are there any questions so far? Okay. So last summer, the IMO 2024 happened. And with it, we managed to see the first time an AI perform to this standard. Here, we can see Google's DeepMind's alpha geometry and alpha proofs framework secure a silver medal in IMO. And furthermore, this wasn't just a silver medal, it was 28 points, 1 point below the gold medal. Also, they scored these 28 points after skipping 2 questions. That means it scored perfect on all 4 questions it solved, including the hardest question in the IMO, of which only 5 humans were able to solve it completely. Now, what we could, but in the end, the alpha proof and geometry couldn't accomplish a complete perfect score. It's due to the inherent limitation in its design, as it's primarily designed for geometry and algebra problems. It can't handle some problems such as discrete mathematics or combinatorics and counting problems. But this remains an open avenue of research that one of my friends is working on here at the U of T Department of CS. And in another area as well, we can see NVIDIA presenting a deep learning method or model called ForecastNet, primarily for climate forecasting. Here, in the top left, we can see ForecastNet predicting the weather 24 months, 24 hours in advance. And when we compare that to traditional methods that you'll find on like Google Weather or the weather station, we can see that it's remarkably similar, almost indistinguishable per se. Now, but this is the only thing, this is not the only thing that this ForecastNet can do. It can also predict the trajectories of these hurricanes and extreme events as well. Here, we have Hurricane Michael tracked by ForecastNet. And we can see here that the true trajectory is well within the expected path it can take as predicted by ForecastNet. What's so interesting about ForecastNet is that these hurricane trajectories can be very chaotic and not well behaved. For example, here, near the beginning, we see it suddenly bends away from Cuba back to the Gulf of Mexico, and then it bends again to Miami again. These subtleties make the inherent problems of weather prediction extremely difficult. It's been said that it's literally impossible to predict the weather two weeks in the future. But what we see instead is that ForecastNet is able to predict these weather events, not just any regular events, but also extreme weather events that can suddenly deflect as well into up to a very high degree of uncertainty, like 4 sigma, which is about 1,000 and 1 in 1,000 chance of happening. And even for those extreme events, it manages to maintain a comparable accuracy to these traditional methods like in these two graphs here, we see that they're well within 0.2% of each other. But what I find is the most interesting about ForecastNet from NVIDIA is that it enables something that hasn't been done before in climate modeling, in that it requires a revolutionary reduction in the amount of compute required to make these simulations. Here, for some context, these traditional methods are generally run on supercomputers. They use these points of comparisons against IFS. IFS is a weather model designed by the European Weather Forecasting Agency and is ran on Pittsburgher. Pittsburgher is the 6th most powerful supercomputer in the world back then in 2020. It's literally like tens of thousands CPUs all together in a rack right next to like some waterfall just for some cheap electricity and cooling. And like whenever these extreme events like these hurricanes happen, they usually take quite a bit of time to predict whether it's going to make landfall or not. And due to this discrepancy, these can cost the public greatly in the end, because due to this delay, this can make the difference between a stay-in-place order or immediate evacuation order, significantly impacting the public near these extreme weather events. So here we can see that IFS, a traditional method, requires 3,000 computers, while ForecastNet only requires 1 computer. This represents a 1,500x speed up over traditional methods. So in other words, instead of owning about $100 million worth of supercomputers, you only need about maybe 1 good computer. Furthermore, for this time to make predictions, we see IFS needs about 1 million seconds or so, while ForecastNet only takes less than 10 seconds. It 45,000 speed up in the end. In terms of energy consumed, given that these are the causes of these extreme weather events, we see a 12,000% efficiency gain. This demonstrates the innovative progress and potential for these novel machine learning methods about tackling traditional problems at hand. For this work, the European Weather Forecasting Agency has recognized the predictions of ForecastNet and includes it alongside its traditional numbers that they'll give you both accounts of the numbers. Here, we see one of the lead research scientists behind ForecastNet recounting the history of it. If we notice the date of publication, it came out pretty much 3 years ago. And in that time, it's seen adoption, at least in Europe. Any questions? Yes?
Delay, just like in terms of architecture, is it plus some error or noise?
This one is what you call a neural operator, and they're doing operator learning. Yes. Now, there's been substantial innovations in operator learning. For example, this computer that they used to run had 4 GPUs in it, but since then, you can reduce the compute even further. I'm now able to run the same simulations on my own laptop, which only has a GPU with 4 GB of VRAM. So instead of having like a supercomputer costing $100 million, you can just get a laptop or a cloud solution for like a couple dollars instead. Any other questions? Okay. Moving on, we have also been seeing some unprecedented success in protein design and generation in the field of computational biology. I would like to recall what a diffusion model is before. What a diffusion model does, it basically creates structure from nothingness, from noise. And one of the common problems in computational biology is the problem of protein design, where biologists have to figure out, like, how should I design my molecule so that it attaches to these target receptors, like the SARS-CoV receptors or some other receptors such as the insulin receptors in diabetics. Such problems are very commonplace and stands in the face of human wealth and human health and well-being in the process. So basically, the team at the University of Washington, the protein design team over there, what they did is they designed a diffusion model called RF diffusion to generate brand new proteins from scratch. And what's so special about these proteins is that each of them have a very high success rate of behaving well and interacting with the target receptors. Here in this animation, you can see RF diffusion generates a brand new protein from nothingness, from just noise, and in that it binds to this insulin receptor, which is affecting the lives of many people in the world this day. For this work, the pharmaceutical industry has recognized it and has began adopting it for their applications. Here we see Sarah Therapeutics has backed the team at Washington and David's lab, Baker's team over there, with over $1 billion of funding, as well as some more other products such as Isomorphic Lab, who does protein folding, a subdivision under Google DeepMind, and with some deals worth up to $1.7 billion, and some more companies from some other hyperscalers as well. Any questions? Yes?
What's the difference between the success of AlphaFold and the latest research?
AlphaFold?
AlphaFold.
Good question. I would say that AlphaFold 3, yes, that's what you're referring to, right? That came out I think about 6 months ago. Since then, when it got released, DeepMind promised that it will be open source, but initially, there's some initial agreements, early agreements, where if you would like to use the weights of the Alpha 3 fold model, you will have to sign an agreement with DeepMind stating that it's purely for academic usage. This is a bit problematic towards these commercial customers, obviously. And so what happened was that the open source community managed to reproduce the results from AlphaFold 3 in a pretty quick manner. So this just talks about the pace of innovation in our field. Okay. Any other questions? And on that note, we also seen some unprecedented success in protein folding and prediction out of AlphaFold 3. AlphaFold 3 is a protein folding transformer baked into a diffusion model. With it, when you give it an amino acid sequence, it can predict the structure of that sequence in the end. And with this, we see a prediction rate of roughly about 95%. In the past, biochemists stressed for and was working hard towards a success rate of just 90% for over 30 years. And for these works, the Nobel Committee has recognized both David Baker's lab as well as Google DeepMind's work for chemistry with a Nobel Prize, along with another Nobel Prize in AI in general towards Geoffrey Hinton here at U of T, as well as John Hopfield at Princeton. What this shows is that the academic committee is embracing these brand new methods for machine learning in hopes of attacking the old problems from before. So, are there any questions? Okay. So, yeah. So with that, I want to go over some overview of general problems in science. But before that, let's take a break for now. Here is a QR code that I would like you guys to scan to fill out availability with the guest speakers. One of them had to change the plan suddenly due to a sudden change in their situation. So we had to go reschedule that. Hopefully this doesn't affect your guys' like exam schedule too much, study habits. Let's resume. But before we do so, does anyone have any more questions? Okay, let's get back to it. So basically, I've shown you guys like what are some of the like applications and use cases of like machine learning and also of scientific machine learning. But to really understand the core of what scientific machine learning really is, we first have to understand what science is to begin with. To me, this is very difficult philosophical question. You can spend your entire degree thinking about it. I won't spend about a year about doing it in my degree. And for me, at least, science is described itself by what kind of problems it can solve. So when you ask yourself what are some kind of problems that scientists challenge themselves with, these generally follow these four general categories that I find. One of the main ones you will see is so-called forward problems, which amounts to basically a prediction or simulation. This is what you usually get taught in like your statistician classes, as well as also physics. But what's the more delicate ones are these so-called inverse problems, where you want to control the behavior of some systems and to find some kind of, and to study some kind of feasibility within them. Afterwards, in a different kind of flavor are these so-called sparsity problems, where instead of just trying to come up with some kind of number or some statistic, you want to come up with some model or law of nature inherent to science that you're studying. This often amounts to discovering new models of physics, detecting some new particles, or just simplifying traditional models in the end. For example, the Greeks believed that the Earth was at the center of the universe, but over time, what scientists discovered is that the heliocentric model, where the Earth was at the center of the universe instead, was often simpler. And via some more experimentation and evidence, it became widely adopted as the standard to go by. So here we can see some kind of sparsity going on. And for like the last kind of category that I want to get into is so-called generation problems. We are, instead of like coming up with some numbers or some kind of law, we want to create something from scratch. So this could be some kind of molecule or some kind of like image or video. These methods are often the most computationally expensive but also represent some of the biggest advantages that benefit humankind from them as well. As for the more general outline for the workshop, I'll be focusing mainly more so on the forward problems, as these are by far the most common problems you'll face in science. This is what the content of the workshop will be for the next month. Our guest lecturers will tackle the problems of inverse, this sparsity problems as well generation, which is highly relevant in the medical industry that you just saw earlier. Okay. Any questions? Yeah.
For forward, would that just be like determining what the parameters will be?
Yeah, pretty much. Yeah. That's also a kind of estimation prediction happen.
Then what would like an inverse problem?
We'll get to there. So here, the first kind of problems that you'll probably see are like these forward problems, which are just usually phrased in terms of like prediction or simulation. Mathematically, they can be written of the form like B equals FA, where A is some input conditions, such as like time, space, or coefficients or geometry. And F is some kind of underlying physical model of the system. Typically, this is like something called PDE. I'll get to that just now. And B is your kind of outcome or result from these two inputs and modeling behavior. These four problems are essential for understanding the behavior of complicated phenomenon. For example, we just saw like the weather prediction that we just saw earlier. This has been an infamous problem in mathematics because it's often said that no one can tell the weather in 2 weeks. And if you can, I'll have good news for you. The Math Institute next door has a $1 million prize for you, okay? Additionally, these four problems are often used as an initial starting point for the three other problems that I just mentioned, like the inverse, discovery, or uncertainty, or generation problems. Here's one example. Here, we have the problem of simulating the strength of underground seismic waves. And for some context, I think about like a week or two ago, there was an earthquake in British Columbia, a 4.7 earthquake. Now, for someone that's lived in the Caribbean, to me, 4.7 sounds pretty weak. That was until I heard that the depth was only 1 kilometer. Then, okay, yeah, that's can be pretty significant. Here, basically, what you want to do, if I want to figure out how bad this earthquake could be, a 4.7 earthquake could be, I would say this is the geology of the Earth's underground. It's composed of many different rock geologies, separated in different stratums with different stone structures, strengths, and weaknesses. And at the weak point, this is where the earthquake is created from some sudden shock that vibrates outwards as a wave. Because of the different composition in the ground, the speed of the wave will change depending on the medium of the stone. This is why there's a color bar representing the speed velocity of the wave. And to model the evolution of this wave and to break the resulting strength at the surface, which is where you will feel it the most as a human, you can model it with something called the wave equation. Using the wave equation, you can see the strength of the wave over time after it was created. Here, your inputs to this model would be the velocity of the wave at the starting point, as well as how it at each particular point in the stone underground. Because due to the complex nature of the geology, we have to keep track of it throughout our entire simulation. And we had to guess it from some initial guess, as well as some initial like source location that we can triangulate with some other means and models. Then, using these initial conditions, since we have a model for how the wave evolves according to this PDE, you can try to solve it according to the PDE to get this resulting strength field of the seismic wave in N. Now, how you actually solve this PDE is a very common problem in applied mathematics and engineering. It's been well studied for the last 50 years or so. There's a slew of techniques to these solutions and predictions. These comprise itself of usually what you call finite element methods or finite difference methods. There's a whole plethora of methods. But what they do in these methods is that they, instead of taking the fine-grained structure of the Earth or of a blade turbine, instead they discretize the surface into a so-called rectangular or triangular mesh, like seen here, with these subtle lines going out throughout the whole geometry. Using this reduced problem, you can apply your computation powers and use numerical linear algebra to solve your partial differential equations to get these simulated outcomes in the end. Any questions? But if the problem with these simulation techniques is that these finite element methods are often computationally expensive in the end, especially when you want to get a high quality result. Here, we have a paper from NASA at the Supercomputing Conference 2022. They were tasked with predicting the SLS launch stage of their new rocket. And what they want to do is trying to figure out how, when the rocket ignites, how the exhaust fumes will spread about in the atmosphere. This has downstream effects on the wildlife as well as neighboring communities. For example, I believe SpaceX is under investigation right now by the FAA, as they did not do any kind of similar analysis to their launch site in Texas. Now, for as to why SpaceX wants to avoid something like that, it's often because the competition is too expensive and takes way too long. Here, to get a high quality result, you require a huge amount of processing power. Often, your initial conditions and data to supply to the model is on the order of 500 million data points, as well as compute requiring the computational power of a supercomputer on for a couple of weeks straight. This is incredibly costly, often laborious. In the end, when you get out your simulated results, you're left with an absolutely huge pile of data, 400 terabytes in this case. What we can see is that these computational techniques often bottlenecked by the current available hardware that we currently have, as well as the problems that they're facing as well in these underlying models pre-described to them. Any questions? Yes? No, what you want to do, this is a prediction problem. So you care about the output in the end. And the resulting output is of the size of 400 terabytes. Your inputs are already at least gigabytes in size, like the mesh geometry, and you want all these fine details as the graph. There's also probably on orders a couple of terabytes as well to begin with. I can tell you a bit of a story from one of my friends. He also went on an exchange to Switzerland. He worked at the Large Hadron Collider over there at CERN. His task was to develop optical data processing computers right next to the LHC, because the reason why they had to do this was because the data being generated at the LHC was so vast that you have to immediately process it, compress it, and then upload it back to your own servers above. And even then, this Switzerland is also always buying new supercomputers just for this very reason. I think his research has now been published now after 2 years in the works. It took a very big team and considered effort to get this problem resolved in the end. So these big data challenges remain a big problem in these traditional computational techniques. Yes?
But then even if it's in a neural network, for example, the reason, like, part of the reason why the mesh is so big is because you're considering the entire space that you're walking with, right?
Yeah, the whole launch site,
Yeah,
yes.
the whole launch site, yes. So in that case, when you're throwing into the network, so let's say we're trying to predict if the tornado is going to hit. So we look at the entire like ocean surface or
Yeah.
whatever, how much like volume when you look at it. Then wouldn't you need to throw all of that information into the neural network as well?
Turns out not necessarily. That's going to be next week's lecture. Okay? So that's okay. And you? You in the back? No more questions?
Since it's boy doing the prediction, what do? They just straight up test, long-term test?
Yeah, pretty much. And the residents in Texas are really complaining about it because it used to be a beachfront property. Now it's basically a polluted wasteland. And I think last night, one of the rockets also failed on re-entry too. Okay. Now, on to inverse problems. These usually amount themselves as some kind of search or control objective. Now, oftentimes, these problems are often differentiable in the model itself. And so one common way to tackle them is to use some kind of gradient descent scheme, like Adam or stochastic gradient descent, or even some second order methods like LBGFS for better speeds, if the problem is amenable and sufficiently small enough to fit on a computer. But however, other times when you know your model is not underlying continuous, like some kind of discrete setting, you may have to resort to like evolutionary algorithms or like Bayesian optimization, or even just traditional like brute force tree search like BFS, GFS, stuff like that. One nice thing about these inverse problems is they often can be rewritten as a optimization problems in itself. Here, what you can see is that since we want B equals to FA, we can move FA to the other side, have B minus FA equals 0, and then we can square them to get to this result. And so in the ideal case, this term should be equal to 0, but due to the missing inputs to the model that we're trying to determine, these are often non-zero, and this is why we seek to minimize A. So when we minimize the input towards the model, we are solving our inverse problem in the end. Some examples of inverse problems include magnetic resonance imaging, called MRI, and image denoising, infection rates estimation, waveform inversion, and optimal shape design. So for those that haven't heard of MRI, this is basically what a so-called MRI machine looks in the top right. You basically stick yourself in a huge magnetic tube and you get scanned during the process. These are very powerful magnets, so you better not have any kind of metals or electronics by you, or else you will seriously risk yourselves. Once you've completed the scan, you get some kind of sinogram that kind of looks like a bunch of superimposed waves. These waves using these waves, you can determine the underlying brain structure backwards via some clever techniques like gradient descent or some kind of other algorithms. Here's the output from this MRI. After it was plugged into an inverse solver. We can see that it's a bit coarse grained. There's lots of missing detail. It's pixelated. Is much lower quality compared to like some kind of direct method in the end. As for another task, you may want to go design an optimal airplane shape if you're Boeing. This helps reduce fuel consumption in the end. So how it goes is that you have something called a Reynolds number that describes kind of the viscosity of the air, depending on some kind of temperature or pressure up in the atmosphere. And then you have some other parameters like the angle of attack and how much lift your engines generate. So given these three inputs, you want to figure out how to best design the shape, where to place the metal to give you this proper shape that minimizes the drag on the plane. This is a very difficult problem in the end. I believe my professor mentioned to me that Boeing spends on the order of billions of dollars to solve these kinds of problems, and they're still lacking behind of Airbus still. So, yeah. Yeah. Any questions? Yeah. It's minimizing the input to the problems. And some other times, in forward problems, you're minimizing parameters into the models so that you have your proper fit in the end. Now, why these inverse problems are a bit different is that these outputs B, you might not even know them. It might not be even given to you. So for each attempt at an inverse problem, you have to do a full forward problem in each try. This substantially raises the cost of inverse problems by few orders of magnitudes. This is why there's lots of money being spent by these like airplane companies as well. Any other questions? Yeah.
So for example, like it'd be like the wave equation, right?
Yeah.
If I want to define the most optimal coefficient, is this how you find the most optimal coefficient?
Yes, you can also use it as well. The thing with the wave equation is we're predicting the strengths. But if you want to predict the speed of the wave, that's technically a parameter. And you can also do that as well as an inverse problem. In fact, you can try both simultaneously if you're really adventurous. Any other questions? Well,
find a difference, or like part of, because the way we put it is linear, so you can just break up into two pieces, and part of it is going to give you the velocity of the person.
yes, but in the case when you don't know the speed of this in the pour stone, it becomes pretty difficult in the end, because you also have to estimate the speed and also the amplitude simultaneously. Yeah, this is why you just have to start off with some initial guess. Like it said, to me, I thought it was going to be something more like 17 kilometers on the ground. But then when I heard 1 kilometer on the ground, oh, that's my initial condition. I'll go with that. And I'll just say it's right under BC capital. Yeah. You also can get like data from like other sensors to help you in your guesses as well. On to our third kind of problem.
Your major, I believe it's like double major. And I played this problem in 7 minutes.
Do I have a question from the chat?
When I was in colleges, Britt Bauer, who is Kelly on the show, she's in here, and she kind of suggested it She was living there and she thought I might be good for Western. And so I applied and I did during students weekend last April. I was like, I love it here. This is perfect. And I committed. I'm really happy that I did. Yeah, it's been so great so far. I've met some really amazing people. I love all of my friends. I've been pretty involved in like student leader, Stuco shows here, both as an actor and like assistant choreographing. I just wrote leaderboard, wave. I'm very excited about that.
Is there a question? Okay, I guess not. Okay. Wait. Yeah, so back to inverse problems. These generally are difficult to solve. In fact, like even the design of these inverse problems aren't really well understood or even make sense at times, which is what I was discussing about. And then another thing is that these like data points are often like scarce or difficult to come by as well. Like in the MRI example, you cannot put a human inside the MRI for any longer, like for like 5 minutes at a time. After which point they're be exposed to too much radiation and you can get sued. And like I said, in inverse problems, you can be in one attempt to solve an inverse problem, you can be solving thousands of forward problems as well. This substantially reduces the cost of them, as making them kind of unfeasible to most people and company. On to our third kind of problem. These are so-called sparsity problems. Usually, these manifest themselves as some kind of idea to be as simple as possible. There's like this quote by Albert Einstein here where he says like, a model could be as simple as it is, can be, but no simpler. In other words, make sure it's the simpler, the better. And we can kind of see that in his work. For example, we all have heard of his famous equation E equals mc squared. Very simple equation. Even a middle schooler can understand it. But the consequences of this equation is enormous. This led to a quantum revolution in physics, as well as also a revolution in gravity, so the so-called special relativity theory as well. Historically, these kind of models F have, which we like to call sometimes the law of physics or natures, have been found through just pure trial and error, or just sometimes just human guessing and intuition. More recently, we've been trying to be more methodological with our theory and experimentation, where when we come up with a model, we test them out in experiments in the real world to find out whether they hold up to scrutiny of nature. And to some extent, this is kind of like solving an inverse problem. Oftentimes, though, the problem skills are often smaller and compared to like the MRI example or the shape optimization problem I just described. But one of the key differences to inverse problems, though, is that the resulting models should be explainable, generalizable, and be able to include novel predictions as well. This can somewhat be seen with ForecastNet predicting the deflections in a hurricane trajectories, which can be extremely rare to observe in reality. Now, how to actually kind of tackle these sparsity problems is that sometimes you use a combination of deep learning and traditional regression from statistics. So first, what you want to do is you want to fit your data to some kind of neural network, and then so-called regress over a library of candidates. This process is kind of similar to that between theoretical understanding and experimentation, where our neural networks represents our theory, and this so-called library represents our experimentation per se. Over here, you can kind of see kind of manifestation of this. We have different kinds of data that we try to model, and then we try to discover the models for each of these functions. Here we see that the data was generated according to this PDE, and what the process learns out and in is something extremely close to the underlying true model. So a bit more details is that the overall structure, you can say, is the PDEs of the form that the change in the time derivative of your function is equal to some coefficient times some kind of observed guess function. These observed guesses could be kind of anything. You could think it could be it could be representative of like speed, acceleration, mass, velocity, but it can also be some other interesting terms. It could be the sine of the wave, the exponential of the wave, or even the logarithm of the wave. What you can do is you can predetermine your guess and just bake it into your data, then derive it from your data, and then try to figure out the underlying coefficients associated to these terms. Now, to determine whether each term is significant, though, is another problem. What this amounts to is we're trying to discover the lambdas which have the highest signal, or in another way to phrase it, the values that are non-zero to these guess functions. In the end, what we want is to find the fewest possible coefficients to the model that are non-zero. Because if they're zero, that means that this term was useless to our experimentation, and we should forget about it in the end. So going back to the problem above here, we see that it only involves this UT, UX, and UXX term, and doesn't involve any UXT term or any UTT term as well. So in this model, these lambda values would be like 0 here and 0 here. For this UX term, this lambda 1 would be 1.002, for example. Now, in this form, you can solve to find the lambda coefficients with the fewest numbers of zeros. This is a so-called sparse regression problem from statistics. It's been very well studied in statistics literature, and there's lots of libraries available to do this in practice. So now comes to the main point of the workshop. What is scientific machine learning? Now, before I go there, is there any questions to the sparsity problem? Yeah. You mean this UXT term? These are just candidate guesses. We're not sure whether they're relevant or not. It's the job of the regression algorithm to determine whether that's the case. Okay, does that make sense? Okay. Okay, so scientific machine learning is a pretty new field. It's only been explored in the last few years or so, and it's seen an explosion of success. recently. We see this immense uptick in publications, much more workshops and tutorials being hosted by these leading AI conferences across the world. And we see many different kinds of topics being handled at the same time. So how I like to think about scientific machine learning is just a combination of science and machine learning together. Because like one of the main weaknesses about machine learning is that it often lacks like interpretability, generalization, and is often computationally expensive in its own right. Like we saw with these like large language models in the beginning of the workshop. On the other hand, science has the complete opposite effect. It's very interpretable. You can extrapolate extremely well once you have a good model, and you sometimes don't even need that much data as well. So this leads to the question of whether we can combine both together to get the best of both worlds. Can we have something that makes theoretical sense, but also experimentally efficient? Can we have a theory that's explainable, but also make novel predictions as well? And this is what we call scientific machine learning. So, yes?
But, so when you're saying that, ML are usually having organization, making like diversity, better, but a lot of the scientific problems are distinct, or rather they don't very much overlap. So how can you argue about generalizing concept?
Yeah, that's true. I would say that also like machine learning technically had the same problem before. Like 10 years ago, when you say you're someone that did like computer vision, your work is very different from some guy that did text and natural language processing. But nowadays, because of recent advances in machine learning, we can often combine both ideas together, into so-called multimodal models or foundation models. And some scientists hope that this same kind of effect can happen as well in science. And this is one of the goals of scientific machine learning. So for one of the lead people behind this is Anima Akbar. She's a research scientist at NVIDIA. And when they produced the initial forecast net, it was pretty specialized to weather prediction, but now they're scaling up these models to the foundation scale as well. When I was talking to these scientists recently at some conferences, they've been telling me that they've been spending a lot of GPU hours on these kind of scientific foundation models. Okay, does that work? Okay, any other questions? Right, moving on. For the rest of the workshop, we'll concern ourselves mainly with two kinds of approaches to and methodologies to scientific machine learning in the context of forward and inverse problems. We'll mainly be focusing on approaches that involve loss functions and architectural approaches as well, quite separately. On the left, you'll see something called a physics loss. These physics laws help add interpretability into our neural networks and help boost training efficiency as well. This is what people like to call physics-informed neural networks, or physics-informed machine learning in more generality. Another approaches are some kind of architectural approaches. These are some things on the analog of like so-called neural operators. These neural operators are very similar to neural networks in that their architectures, while mostly the same, has some key fundamental differences that enables it to encode more symmetry of the underlying data, have better conservation to the underlying structure, and is better well behaved and tackling. In the end, these helps tackles the problems that we faced in both separate fields at once. Now, as to some more specific topics we might learn about, there's many different areas to choose from, but we will focus mainly about Fourier neural operators, which is the backbone behind ForecastNet, and also physics-informed neural networks the week after. Our guest lecturers will be talking about some regularization techniques, as well as AlphaFold in the BioML context that will be handling protein design, and computation, and creation. Now, each of these topics have some well-established literature in them, applied to basically all those four kinds of problem tasks that I showed you earlier. And over the course of the workshop, we'll be tackling into some of these more notable ones that caused a huge impact in the field recently. Furthermore, these two approaches have their own trade-offs as well. For one, we can see that these loss functions approaches have a bit more, let's say, data requirements, and also a bit more, but also comes at a cost of more constraints. So when you do physics-informed machine learning, you reduce your data requirements, but you increase your optimization complexity instead. Whereas if you want to do a neural operator approach, you often need high amounts of data, but this comes at a cost of flexibility, of extra flexibility. So usually to get this extra kind of data, you run traditional simulations like finite element methods to generate your raw data to help feed into these models as well. This reduces one of the significant challenges faced in these foundation models like ChatGPT, where nowadays people and experts believe that it's not that GPUs are one of the main bottlenecks to foundation models, but rather data is the main bottleneck behind foundation models these days. This is pretty much a paraphrase of Ilya Sutskever's talk at NeurIPS recently in December. So onto the roadmap for the workshop in the coming weeks. Next week will be an introduction to neural nets and deep learning. Once that introduction has been finished, we'll move on to operator learning and neural operators. That'll be the focus of next week. After that, we'll be heading into physics-informed neural networks and physics-informed machine learning, where we'll be covering some of the frameworks and optimization problems that we see there. For the last week of March, we'll be getting our hands on with coding up both approaches in PyTorch, and I'll be giving you some sample code to help guide you guys along the process with that. And then I hope you guys fill out the QR code so that we can schedule our guest lecturers on their respective topics as well. Thank you. Any questions? What about them would you like to know? Well, when you do these numerical methods, they're usually specialized to some specific tasks. Like this one here, this meshing problem is strictly 3D based, 3D geometry based. If you want to do something like two-dimensional, you have to completely change up your approach and algorithms. These foundation models offer the flexibility to handle different kind of modalities at the same time. Possibility, higher resolution, higher dimensions, and different fidelities or quality. Like, look, this is a fine meshing. And if I want to go change the material, it would have to go be re-simulated in like a finite element method. But if we have a well pre-trained foundation models, we can just do inference instead of just retraining the foundation model, which is quick in context relative to the finite element method. Yes. And there is some, yes. A bit more, another example from ForecastNet is that ForecastNet actually had a lower quality data than what was available to the supercomputer center at Europe. ForecastNet only had access to a resolution of 30 by 30 kilometers, while the traditional methods have higher fidelity data at 18 kilometers. Basically, they had about nearly, I think, 3 times the data based on these resolution counts alone. And despite of that, we can see only a slight modest increase in cost of only tripling. But any other questions? Yes. They have their ways, the media. But it's nothing too bad. It's just mostly traditional deep learning methods, to be honest, combined with some insights from science. Yeah. So one thing that they didn't do in this 2022 model is they didn't count for the spherical structure of the Earth. They just treat it as like a flat latitude and longitude grid. This obviously can cause some artifacting by the north and south poles if you really want to stare at the animations. Now, but on the other hand, you can account for the spherical geometry of the Earth and embed that into your neural operator so that it can easily handle the spherical geometry in the end. And this is how I was able to replicate the same performance on my own computer in the end. It's only 4 gigabytes of VRAM compared to like 200, I think, or something. Yeah. Any other questions? Yeah, I guess we can wrap up now. And just make sure to fill out this link in the end, okay? It will help to organize the conference later and to help you guys figure out your study plans for your finals as well. Okay, thank you.
Thank you.